Welcome, self-learners, back to learning as a hobby. And as I promised, I'm going to start today with single variable calculus. Remember, I'm going to be doing 3 classes during this, quote, semester, single variable, multivariable, and physics 1, I guess. And we'll get to the other 2 classes after I do chapter 1 here. So I'm going to start with single variable calculus today. If you recall from my vlog, if you watched it, if you haven't seen it, you can go to the YouTube page and watch it there. It's up for anyone to see. But I'm going to be going through part 1, chapter 1 in the book Calculus by Michael Spivak, and I explain everything about it in that vlog, so you can go check that out. But what I'm going to do is I thought I'd start by reading the introduction to the book and then going through chapter 1 in the book, or my notes at least, where it's basically me just summarizing what he talks about in chapter 1, and then I'll make a separate video for the problems that I'm going to do from chapter 1. So let me start with the introduction and the beginning. He has a nice quote by Francis Bacon. I'll read that to you first. I hold every man a debtor to his profession, from the which as men of course do seek to receive countenance and profit, so ought they of duty to endeavor themselves by way of amends to be a help and ornament thereunto. And I hope that my videos satisfy that as well. So let me start by reading his preface, and then, like I said, I'll just summarize chapter 1, what he talks about, and do some of the important proofs and stuff that happen in that chapter. The summary that I'm going to show you guys is not a supplement for reading, or I should say, you should read chapter 1 yourself in the actual book, because the summary doesn't capture all of the details and everything and his writing and everything. So, but anyway, here's the preface. And this is the first preface, the preface to the first edition. There's also a preface to the second edition and third and fourth edition, but I'll just read the first one. Every aspect of this book was influenced by the desire to present calculus not merely as a prelude to, but as the first real encounter with mathematics, since the foundations of analysis provided the arena in which modern modes of mathematical thinking developed. Calculus ought to be the place in which to expect, rather than avoid, the strengthening of insight with logic. In addition to developing the student's intuition about the beautiful concepts of analysis, it is surely equally important to persuade them that precision and rigor are neither deterrents to intuition nor ends in themselves, but the natural medium in which to formulate and think about mathematical questions. This goal implies a view of mathematics which, in a sense, the entire book attempts to defend. No matter how well particular topics may be developed, the goals of the book will be realized only if it succeeds as a whole. For this reason, it would be of little value merely to list the topics covered, or to mention pedagogical practices and other innovations. Even the cursory glance customarily bestowed on new calculus texts will probably tell more than any such extended advertisement, and teachers with strong feelings about particular aspects of calculus will know just where to look to see if the book fulfills their requirements. A few features do require explicit comment, however. Of the 29 chapters in the book, 2 starred chapters are optional, and the 3 chapters comprising part 5 have been included only for the benefit of those students who might want to examine on their own a construction of the real numbers. We will do all of those things, by the way. Moreover, the appendices to chapter 3 and 11 also contain optional material. The order of remaining chapters is intentionally quite inflexible, since the purpose of the book is to present calculus as the evolution of one idea, not as a collection of topics. Since the most exciting concepts of calculus do not appear until part 3, it should be pointed out that parts 1 and parts 2 will probably require less time than their length suggests. Although the entire book covers a 1-year course, the chapters are not meant to be covered at any uniform rate. A rather natural dividing point does occur between parts 2 and 3, so it is possible to reach differentiation and integration even more quickly by treating part 2 very briefly, perhaps returning later for a more detailed treatment. This arrangement corresponds to the traditional organization of most calculus courses, but I feel that it will only diminish the value of the book for students who have seen a small amount of calculus previously, and for bright students with a reasonable background. The problems have been designed with this particular audience in mind. They range from straightforward, but not overly simple exercises, which develop basic techniques and test understanding of concepts, to problems of considerable difficulty and, I hope, of comparable interest. There are about 625 problems in all. Those which emphasize manipulations usually contain many examples, numbered with small Roman numerals, while small letters are used to label interrelated parts in other problems. Some indication of relative difficulty is provided by a system of starring and double starring, but there are so many criteria for judging difficulty, and so many hints have been provided, especially for harder problems, that this guide is not completely reliable. Many problems are so difficult, especially if the hints are not consulted, that the best of students will probably have to attempt only those which specifically interest them. From the less difficult problems, it should be easy to select a portion, which will keep a good class busy but not frustrated. The answer section contains solutions to about half the examples from an assortment of problems that should provide a good test of technical competence. A separate answer book contains the solutions of the other parts of these problems and of all the other problems as well. Finally, there's a suggested reading list to which the problems often refer and a glossary of symbols. I'm grateful for the opportunity to mention the many people whom I owe thanks. Actually, and then he just thanks all the people, so I won't really talk about that. It might be worth, maybe I'll do this in the exercise video that I'll do. So when I do the exercises for chapter 1, maybe I'll do the suggested readings that he has here in the appendix. So, but anyway, that's the preface. And there was something else I wanted to mention. Oh, the separate answer book. I mentioned this in the vlog, but I'll say it once more since this is uh, the start of the series for, Michael Spivak's book on the channel. There is a solutions manual to the book, which you can purchase online if you want to, just so you know that it's available. I always try to avoid using solutions manuals unless I'm like completely stuck and I've exhausted all efforts to try, solving a problem, and it still remains a stumbling block or whatever for me. So, and I suggest that if you're trying to learn math on your own, that you adopt the same technique. Try not to use solutions manuals unless it's absolutely necessary. Or if you already feel like you finished solving the problem and you want to see how the authors do it. But it doesn't, having a solutions manual and just looking up the answers uh, is sort of counterproductive. So I suggest that you do your best to try the problems yourself on your own before looking at solutions. And I'm just speaking from experience. This is, if you want to make the most out of the problems in the textbook, you have to do it that way. Otherwise, you're kind of just wasting your time. So, but just be aware there is a solutions manual if you want it. All right, so let's go to chapter 1, and actually I'll bring up my notes here because I'm not going to show you the chapter 1 in the book. And like I said, this is just a summary. So these are just my notes for that I took on chapter 1, and it's very abbreviated. Like I said, I do suggest actually getting the book and reading through it yourself, because there's a lot of, he's a good writer, Michael Spivak, and there's a lot of details that obviously I can't get to in a summary, and you'll miss his sort of clever, witty dialogue and stuff. So let me bring up my notes though, and we'll go through some of the important stuff. Okay, so first thing is, this is part 1, chapter 1, very first part of the book, and he recommends that you do in the text itself. He recommends that you do problem 5, problem 24, and problem 25 to elucidate some of the things that he's talking about in the chapter proper. So I'll definitely be doing these 3 problems when we get to the video on the problems for chapter 1. And then I may also add like 1 or 2 problems that are just interesting to me, or that I find particularly fun to solve or something. So that video will be a separate one though. So right now I'm just going to go through the notes for the chapter 1. All right. So what he does in chapter 1 is establish what the field axioms are for example, the real numbers. He doesn't say it, he just calls them numbers, but if you don't know, the real numbers form something called an ordered field, actually a complete ordered field, but he avoids talking about completion in chapter 1 because he's going to get to that later on. But he goes over the field properties, which I have listed here, P1 all the way up to P9. These are the field axioms. These are the axioms that, it's sort of like the logic of how real numbers work, and they allow you to solve equations and things like that, all the stuff that you did in like an elementary algebra course. And once he gives you the axioms, he asks you to, let me see if I can get a marker to work here. After he goes over the axioms, he asks you to like show these things. He does show them in the text proper, but I want to actually do it for you. I think it's worth seeing that done in person, just so you can get a feel for how, to use axioms to prove things about numbers and stuff, how that works, especially if you've never seen it before. If you have taken some advanced math courses before, these are the kinds of things that you see over and over again, and it kind of gets to be a bit tedious. But you should do it once in your life, and I'm going to do it again after I've done it many, many times in my time in school. But I'll do it again for you guys just so you can see. But you should try these also on your own before you watch me do it. When you're reading a math textbook, you have to be active. You can't just, read passively. You have to actually do the proofs yourself and so on. So try it out yourself before you look at someone else's solution. So I'll prove these for you guys in a minute. I just want to show you all the stuff that he goes over in the chapter, and then I'll prove all the stuff that he wants you to prove. Or actually, before I even do that, let me just go to the field axioms for a second. Maybe I should say what they're called. P1 is called an associative law. This is the associative law for addition. You can see that the operation we're looking at is addition. And what the associative law tells you is it doesn't matter if you're doing a sum. It doesn't matter if you add b plus c together first and then add a to it, or if you add a and b together first and then add c to it, you still get the same number. So that's a property of real numbers. That's called an associative law. There's also an associative law for multiplication, which you can see in P5. P1 and P5 are associative laws. Okay. Then we have some commutative laws. Maybe I'll just highlight these in different colors. P2, not P2, sorry. P4 and P8 are commutative laws. P4 is a commutative law for addition, and P8 is a commutative law for multiplication. And commutativity just means that it doesn't matter the order that you add numbers together. So if you add a plus b, that's the same number as b plus a, and same thing for multiplication. A times b is the same thing as b times a. So the green ones are examples of commutative laws. All right, then you have, let's see, what color should I use next? Maybe I'll do blue. Then we have P2 and P6. These are existence of identities. Of identity. So meaning 0 is called the additive identity. It's called that because when you add 0 to any number, it doesn't change the number. So, any real number plus 0 is still that real number. And there's also a multiplicative identity, but it's a different number. It's 1. And notice that he does make a note on the side that 1 is different than 0. And that may seem weird, but you do actually need that. Because if you allow, there are some cases where if you can allow 1 to be 0, but it sort of destroys the size of the set. It makes everything equal to 0, and we don't want that, especially for the real numbers, because that's not what the real numbers are. So the multiplicative identity is different from the additive identity. right? And one is the multiplicative identity because when you multiply any number by it, it doesn't change it. So any number times one is still that same number. So those are existence of identities. And then you also have, let's see, what color should I use next? Maybe orange. P3 and P7 are existence of inverses. So P3 talks about the existence of additive inverses for every real number, and P7 talks about the existence of the existence of multiplicative inverses for multiplication. And all that means is, for example, for addition, if you have a real number, if you add its additive identity to it, you always get 0. For example, 2 plus -2 is 0, right? That's -2 is the additive inverse of 2, and vice versa. 2 is the additive inverse of -2. And you also have multiplicative inverses. And notice again, you do have to state a not 0 because of the fact that allowing 0 to have an inverse destroys everything. If you remember back to your algebra courses, we always, for real numbers at least, we say division by 0 is not allowed. It's undefined, right? For P7, this is for multiplicative inverses, and just to give an example of that, 1/2 is the multiplicative inverse of 2, because if you multiply 1/2 by 2, you get 1, which is the multiplicative identity. Okay, and vice versa, right? 2 is the multiplicative inverse of 1/2. Okay, so those are the orange ones are existence of inverses, and then you have one other law that's sort of over by itself. Maybe I'll do that one in purple. And this one sort of connects everything together. This is a distributive law. And this connects, addition and multiplication together. So if you multiply the sum B plus C by A, that's the same thing as multiplying B by A and C by A and then adding them together. So that's called a distributive law. All right, so these are the field axioms for the real numbers, or it's just actually field numbers. There are other fields other than real numbers, but in calculus, we'll be looking at real numbers. So that's the first thing. And if you remember what I mentioned just a minute ago, the real numbers are more than just a field. They're an ordered field, which means that there's an order to them, right? Some numbers are less than others and so on. So let me get to those axioms next, which is the next thing that he talks about in the book. And maybe I'll change back to red. Okay, first we start with a definition. Let P be the set of all positive numbers, and then you can use that to define inequalities. So this is called the trichotomy law. This is axiom 10. For every number A, one and only one of the following hold. So either A is 0, or A is a positive number, or negative A is a positive number. So for example, 1 is in the set of positive numbers because it's positive, but -1 is not. But -1 is in the set of positive numbers. Okay, so one of these three things is true for every real number. Well, only one of these things, one and only one. Right? And then we also have some closure properties for the set of positive real numbers. The set of positive real numbers is closed under addition, and it's also closed under multiplication. What do I mean by closed? What I mean is if you take any two positive numbers and add them together, you still get a positive number back. If you take two positive numbers and you multiply them together, you still get a positive number. That's what it means to be closed under those operations. All right, and using this notion of the set of positive numbers, like I said, we can define inequalities in terms of that set. So A greater than B means that A minus B is a positive number, right? Or, for example, A less than B means the same thing as B greater than A. A greater than or equal to B means A is greater than B, or A is equal to B. The less than or equal also includes the case where they are equal. And same thing for A less than or equal to B. That means the same thing as A less than B, or A is equal to B. Right, and then also A greater than 0, if A is greater than 0 if and only if A is in the set of positive numbers. All right. And from that definition, we get another version of the trichotomy law, but posed in these different senses. So here, from P10 to P12, this is equivalent to the trichotomy law, and so is this. And you can use the either or either of those representations. All right, and from there, they want us to prove some things. They want us to prove transitivity, which I'll do, and then they want us to prove this as well. So let's do that right now. Oh, actually, did I say I was going to do the proofs later? I think I'll wait. Yeah, let me go through everything first, and then I'll do the proofs after. So we'll hold off on proving transitivity and that other thing for a minute. All right, we have some more definitions down below. This is the definition of the absolute value. If you remember back to your algebra course, they probably gave you a geometric definition for the absolute value. They probably also gave you this piecewise definition, but I'll say it again here, and because he does in the text. So the absolute value, which is you use the symbol to denote it. So it's sort of like two vertical bars around the number, and the absolute value is equal to the number if the number is positive or 0. But if the number A is negative, then it's equal to the negative of A. So here, that's what this is saying. If A is less than or equal to 0, if it's negative, then the absolute value is equal to the negative of it. That might sound confusing at first, but if I give an example, it might make it clearer. So for example, the absolute value of 3 is just the number itself, because 3 is greater than or equal to 0. Whereas the absolute value of -3, since -3 is less than or equal to 0, this is equal to -3, which is +3. So notice in both cases, you get a positive number. It's sort of like the distance from that number to 0. That's the geometric definition that they give you in algebra. So just to think about it intuitively. All right, so they give us that definition, and then right after that, he uses the absolute value to write down a theorem. This is called the triangle inequality. And it says for any real numbers A and B, the absolute value of A plus B is always less than or equal to the absolute value of A plus the absolute value of B. All right, and he does prove the theorem in the book, but like I said, I'll do the proofs for you as well. So let's actually do them right now. We'll do all the proofs that he does in the text proper. And there's quite a few things that he does, so this might take a little bit of time, hopefully not too long. And I guess I'll prove them on the whiteboard here. This way it'll be easy to write. So I'll start with these things that he wants us to prove, this, and then I'll go on to the other ones that he has below. Okay, hopefully it's not too difficult to read my writing. So let me go to the whiteboard that they have on Zoom. Okay, and then we can use this to prove. Let me see. Draw. Okay, so let's just go down the list and prove everything. So he wants us, the first, like I said, that first group of things that he wants us to prove involve using the field axioms to prove certain statements. So the first thing that we'll do is this. So prove. Oops, my pen doesn't seem to want to work anymore. Proves that for all real numbers, Why is this not working? For all real numbers, a, if a plus x equals a, come on, then x equals 0. So this is sort of like a feature that characterizes the number 0, right? Again, if you add anything to 0, it doesn't change the value. Using the first 3 axioms, we can do this. All right, so here's the proof. And I'm sorry that I'm writing so slow. It's because for some reason there's a lag in the pen that I'm using, the XP pen. All right, so for all real numbers a, if a plus x equals a, then x equals 0. So we'll do this with a direct proof. And I'm realizing now that actually that now that I'm getting into proofs, maybe I should make some videos on proof techniques because some people that are watching these might not know those. But anyway, if you want to look up a direct proof, that's what I'm going to use here. I'm going to prove this with a direct proof. All right, so let a be a real number. And let a plus x equal a. Then by the existence of additive inverses, so by P3, there exists, come on, this is so annoying. There exists an additive inverse, which I'll denote like this, negative a and r. Maybe I should define these symbols in case you've never seen them. This stands for the set of real numbers. And this symbol means is an element of. So this little bit of symbols means negative a is an element of the real numbers. So there exists an additive inverse for a. Okay, so from that, and actually I'll erase this just so it's not cluttered. Okay, so we can add negative a to both sides of this equation here. So a plus x equals negative a plus a. So I'm just adding equals to equals, which still preserves equality. And then I can use P1, the associative law for addition. So by P1, I can just reassociate negative a plus a. Oops. Plus x equals 0. So on the right hand side, that's equal to 0 by P. What is it? P3, I think it was. So actually, maybe I can write it up here. This is equal to 0, and this is by P3. Okay, and again, negative a plus a is 0, so we get 0 plus x is equal to 0, so x is 0. And that's the end of the proof. So if you see me draw a little box like this, that's what that means, end of proof. Okay, so that shows that this statement here, oops, is true for all real numbers. Okay, so let's go on to the next thing he wants us to show. I'm just going to go down the list. Like I said, he does it in a more literary and entertaining way in the textbook. This is sort of like just a summary of everything he did. The next thing I want to show is so prove for all non-zero real numbers, AB times AC. I'm sorry, AB equals AC. Then, sorry, there should be if. Sorry, if AB equals AC. Actually, let me just make it look a little nicer. If AB equals AC, then B equals C. Right, and again, we can use it. We can prove this using the axioms, the field axioms. Right, so if we assume that A is a real number that's not 0, so let A be an element of the real numbers. Oh, come on. Hang on. Okay, let A be an element of the real numbers minus 0. And AB equals AC. Then A not 0 implies, come on. Implies that there exists a multiplicative inverse of A. Okay, that's by, what was it, P? I forget which number axiom it was, just the existence of multiplicative inverses. Then there exists an A inverse in R. So if we take this equation here and multiply both sides by A inverse, again, if you multiply equals by equals, it doesn't change the equality. And we can use the associative law for multiplication. So just reassociate. And then A inverse times A is equal to 1 by the definition of a multiplicative inverse. So we get 1 times B equals 1 times C. And if you remember, there was another axiom that said 1 is the multiplicative identity. So when you multiply anything by it, it doesn't change the value. So 1 times B is the same thing as B. 1 times C is the same thing as C, so we get that B equals C, which is what we wanted to conclude. So that's the end of that proof. So really kind of simple, sort of seemingly obvious things, I guess. But the point of doing these is just to get used to axiomatic systems and how you could use axioms to build up the properties from there. So that's the next thing on the list. Again, I'll just keep going down the line. The next thing I want to show is A, B, so prove prove A, B, or sorry, actually, let's do this first. For all real numbers, A times 0 is 0. Right, so when you multiply anything by 0, it gives you 0 back. All right, so to prove this, we're gonna, again, we'll do this with using the axioms. So we'll start with let A be a real number. And I don't know why Zoom is being so weird with my XP pen right now, but I'm doing my best. I hope it's not too distracting. So let A be a real number. Consider A times 0 plus A times 0. And using the distributive law, this is the same thing as A times 0 plus 0. So I just distributed out, factored out the A. And then 0 plus anything, remember, doesn't change the value. So 0 plus 0 is just 0. So this is A times 0. Right, and so we have the new equation A times 0 plus A times 0 is A times 0. Okay, and now there exists an additive inverse for A times 0, so we can add that to both sides of this new equation. So negative A times 0 plus A times 0 plus A times 0 equals negative A times 0 plus A times 0. Okay, and this is equal to 0 by the definition of an additive inverse. And I can reassociate on the left-hand side. So this is by additive inverse. I forget what number it was in the list, but and then I can reassociate here, so I can take the parentheses and move them. On the left-hand side, okay, that's equal to 0. And then again, by the additive inverse property, this thing in the brackets is 0. And remember, when you add 0 to anything, it doesn't change the value. So this says that a times 0 is equal to 0, and that's what we wanted to show. Right, and that's using the distributive law and the fact about additive inverses. Okay, next thing on the list, prove if a times b is 0, then a equals 0, or b equals 0. Right, so let's do that again using the axioms, just the field axioms. So proof so assume a is not 0, and that I should say without loss of generality here, because there's symmetry in the hypothesis for this proposition. So it doesn't matter if you let a be not 0 or b not be 0. Like I said, maybe at some point I'll do like a video series on proof techniques. Right now I just want to go through the proofs. So without loss of generality, assume a is the one that's not 0, and that ab equals 0. Right, so if a is not 0, then its inverse, its multiplicative inverse exists, right? So a not 0 implies, come on, Zoom, implies a inverse exists. So if AB is equal to 0, I can multiply both sides by a inverse, and I can reassociate on the left-hand side by the associative law for multiplication. And from the fact that we just proved before, a inverse times 0 is 0. So here we get 1 times b is 0. So b is 0. Okay, and obviously if a is equal to 0, you get 0 from the last thing that we proved. So if a equals 0, then a times b. Oh, if a equals 0, then it's already satisfied. I don't even have to write this. Then done. All right, so that's the proof of that. Next, let's see, what does he talk about next? Yeah, I'll do this one. Prove a minus b equals b minus a implies a equals b. Okay, so again, just using the axioms, so proof assume that this is true. Right, then we can let's see, we could add a to both sides. Right, and the right-hand side, I can just switch things around by the commutative law for addition. Then I can use the associative law on the left-hand side. And on the right-hand side, I can use associativity again. So here you get minus a plus a. Remember, minus a plus a is 0. So on the right-hand side, we just get b. Right, and I'll add b to both sides next. So a plus a minus b plus b is equal to b plus b. And on the right-hand side, I can reassociate rather. Right, and remember that minus b plus b is 0, so I get a plus a equals b plus b. And then remember that this is the same thing as a times 1 plus a times 1 equals b times 1 plus b times 1. Okay, and then I can factor out a using the distributive law. And on the right, I can factor out b, again, using the distributive law. And then 1 plus 1 is not 0, so I can divide both sides by its inverse. And I'm running out of space, so I'll just skip that step. And from there, you get a times 1 equals b times 1, which is a equals b, which is what we wanted to show. Just don't forget that I didn't write it down, but in this step, you have to multiply, just because I'm running out of space, multiply both sides by 1 plus 1 inverse. So by the multiplicative inverse. Okay, the next thing is, and I realize these probably seem kind of tedious, and they are. There's nothing really glamorous about these, but it is important to do these at some point in your life. So negative a times b equals negative a times b. Right, so that's what we want to show using the axioms. All right, so let a and b be real numbers. So consider negative a times b. So I want to show that this is the additive inverse of a times b. So what I'm going to do is add a times b to it and see if I get 0. Right, and here I can notice by the distributive law, I can factor out b from both of the terms. And remember that negative a plus a is 0. And we know that 0 times anything is 0. Okay, so I have this equation now, negative a times b plus a times b is 0. And I can multiply both sides. Sorry, I can add the multiplicative inverse of a times b on both sides. Sorry, did I say multiplicative inverse? I meant additive inverse. Plus a times b plus minus a times b equals 0 plus the negative a times b. And again, 0 plus anything doesn't change the value, so this is minus a times b. And we can reassociate on the left-hand side. All right, that's equal to negative a times b. And again, a times b plus the negative a times b is 0. They're, additive inverses. So negative a times b plus 0 is equal to negative a times b. And again, adding 0 to anything doesn't change it. So this is the same thing as negative a times b on the left. And that's equal to negative a times b. And that's what we wanted to show. Okay, moving on. The next one is we want to show that when you multiply two negatives together, you get a positive. So negative a times negative b. We want to prove this. Is equal to a times b. Right, so we want to show that negative a times negative b is the same thing as the additive inverse of negative a times b. So I'll add those two things together. So I'll omit writing let a and b be real numbers, just because hopefully you understand that at this point. So negative a times negative b plus negative a times b is equal to, by the last thing that we proved, this is the same thing as negative a times negative b plus minus a times b. And I can factor out the minus a using the distributive law. Oops. And again, minus b plus b is 0, so you get minus a times 0, which is 0. Okay, so that gives us the equation minus a times minus b plus negative a plus times b is equal to 0. And I can add the additive inverse of negative a plus b to both sides. Okay, so plus a times b equals 0 plus a times b. Right, and we can reassociate negative a times negative b negative a times b plus a times b is equal, remember when you add 0 to anything, it doesn't change the value, so this is a times b. And here we get negative a times negative b plus 0 equals a times b. But again, when you add 0 to anything, it doesn't change the value, so we have negative a times negative b equals a times b. Okay, so that's, let's see, is that the end of the things for the field axioms? I think so. The next two are just for when he went over the axioms for the order properties. So let's do those two next. And then there's one theorem that we need to prove. All right, so here, this is called a transitive property. We'll do it for less than. Right, so in symbols, what that means is if A is less than B and B is less than C, so if then A is less than C. So that's transitivity for less than. So let's prove that using the way that we defined less than in terms of positive numbers. So let the hypothesis be true. Let A less than B, B less than C. Then by the definition of less than, B minus A is in the set of positive numbers, and C minus B is in the set of positive numbers. Okay, and by the closure of the set of positive numbers under addition, that means that B minus A plus C minus B, which if you notice simplifies to give you, because the B and the minus B cancel to give you 0, this is equal to C minus A. But notice that the left-hand side is definitely in the set of positive numbers, because when you add a positive number to a positive number, you get a positive number. But since that simplifies to C minus A, this is also in the set of positive numbers. And by the definition of less than, that means A is less than C. And that's the proof. Okay, and then what's the next thing they wanted us to show? Oh yeah, okay, so the product of two negative numbers is positive. Let's see, can I fit this in? Maybe I can fit this in on this one page. I don't know, why should I? It's not like I'm gonna run out of screens. Let me go to the next one. All right, so here, this is what they want us to show. Prove A less than 0, B less than 0, then A times B is greater than 0. All right, so let's do that. So assume that the hypothesis is true. So assume A less than 0, B less than 0. Then by the definition of less than, that means that negative a is in the set of positive numbers, and negative b is in the set of positive numbers. Consider negative a times negative b. And from that last thing that let me go back to it. From this statement here, negative a times negative b is a times b. And this simplifies. This is greater than 0 because actually, maybe I should write that in terms of the positive numbers. This is in positive numbers by closure of the set of positive numbers under multiplication. Right, but we know that negative a times negative b is a times b, so that means, so negative a times negative b is a times b is in a set of positive numbers, and that means that a times b is greater than 0, and that's the proof. All right, so those are all like the little things that he does in chapter 1, involving using the axioms to prove other properties of numbers. There is one big theorem in chapter 1 in part 1, which is the triangle inequality. So I'll prove that one last. And like I said, I'll still be doing some of the exercises from chapter 1, but in a separate video. This video is long enough as it is. So the theorem that we want to prove here is called the triangle inequality. This is called the triangle inequality. And it says, so if you let a, b, and c be any real numbers, then the absolute value of a plus b is less than or equal to the absolute value of a plus the absolute value of b. All right, so that's what we're going to prove. And in order to, there's a few ways that you can, actually, there's many ways that you can prove the triangle inequality. I'm going to use the long way by doing cases, but there are more efficient ways of proving the triangle inequality. But this is the way that I'm going to do it. So if you're interested in seeing other ways, you can either look it up, or if you want me to do them, you can ask me to do it too. But I'm going to use cases here. So proof. All right, so by cases. So there's two easy cases. The first case is assume that a is greater than equals 0, b is greater than equals 0. Then a plus b greater than equals 0, which implies that if you look at the absolute value of a plus b, just using the definition of absolute value, that piecewise definition, that's the same thing as a plus b, right? But since a and b are greater than or equal to 0, that's the same thing as their absolute values summed together, and we can replace these with less than or equal. It's the same thing, right? The next easy case is assume that they're both negative or 0. So assume A less than equals 0, B less than equals 0. Then that means that negative A is greater than equals 0, negative B greater than equals 0. And then that means that negative A plus negative B is greater than or equal to 0. And if we consider the absolute value of A plus B, then by the definition, this is this, the piecewise definition of the absolute value. This is the same thing as minus A plus B. And if I distribute, it's the same thing as minus A plus minus B, which is the same thing as absolute value A plus absolute value of B. And again, if we want, these all can be replaced with less than or equal. So that takes care of the two easy cases. The next case is just a little bit more involved, but I'll say so for case 3, you can do this without loss of generality. So without loss of generality, assume that A is greater than equal to 0 and B is less than or equal to 0. So they have opposite signs. Okay, one is positive, one is negative. Okay, then there's two things that can happen. So maybe I'll do this, I don't know, I'll do these sub cases as well. Then either A happens, which is that A plus B is positive or 0. Okay, if that's the case, then if you look at the absolute value of A plus B, this is the same thing as A plus B. Okay, and since B is negative, so maybe let's see, I'll make a note of this on the side, maybe, or actually, maybe I'll write it up here. B less than or equal to 0 implies B less than or equal to minus B, because negative B is positive, right? If B is negative, right? So then this is less than or equal to A plus minus B, which is the same thing as the absolute value of A plus the absolute value of B. Okay, and that checks out. And then the other case is A plus B less than or equal to 0. Okay. So then let's see, if we consider A plus B an absolute value, this by the definition, this would be negative A plus B, which is the same thing as minus A plus minus B. Right? And because A is positive, again, I have to make a note here. Negative A is less than A since A is positive. Okay. Maybe actually, that might be hard for people to follow. So actually, let me say A greater than or equal to 0 implies minus A less than equal to A. Right, so this is less than or equal to A plus minus B, which is the same thing as the absolute value of A plus the absolute value of B. Right, and case 3 exhausts both the cases where one is positive and one is negative. You can do it without loss of generality, but because of symmetry. So that's the end of the proof, and that proves the triangle inequality. All right, and that's basically all the things that he proves and talks about in chapter 1. So like I said, you should try these all yourself and make sure you can do the proofs and you understand them. You should definitely read through the chapter if you have the book. And like I said, I'll be doing some of the exercises from chapter 1 in the next video. So once I, do them myself, and then I'll make the video on it and talk about, like I said, just a few of the exercises. There's a lot of exercises, so I'm not going to do all of them, but I'll pick the ones that he told us to do in the chapter. I think it was 5, 24, and 25. And then if I find some other problems in the section that I like or that are interesting, I'll do those as well. All right, guys. So let me just stop the screen share for a second. Thanks for joining me today. That was chapter 1 in Calculus by Michael Spivak. Look out for the next video, which will be the exercises for chapter 1. And then after I do that, then we'll do chapter 1 in Schifrin's book, the multivariable mathematics, right? And we'll go do chapter 1s and all of them, and then we'll move on to chapter 2 and so on. All right, guys. So I'll see you in the next video, and I hope you enjoy learning.